All right. Let's go ahead and start for today. So today, what are we going to be dealing with? Well, we do some ion stuff. Let's for a second. And 1 second. We're going to talk about Wednesday class. Let me do some more stuff with ions and ionic nomenclature. Hopefully we get to covalent bonds. We're having some issues with the ions, so I want to go back over that again. Wednesday. So, Wednesday I will not be available. The bigger problem is I won't be available to have a procedure right between when my morning class and my afternoon class starts, so I'm going to be out all day. Good news is we did not have a lab planned for Wednesday. If you, by the way, can someone take that door closed? Just leave the door stop in it so it's like cracked. It's not even there, it's supposed to have the door closed. I wouldn't be able to be here anyway. We don't have a lab scheduled for this week anyway, so that's good. Not going to lose a lab. The next lab doesn't really fit until we get into the next unit, so that's fine. Lecture. So, I think we'll do an online presentation. It's going to be the end of this material, so it's going to be stuff we're going to cover today and then add a little bit at the end, because I want to add, technically after covalent, the only thing I really need to add is polyatomics, which we're going to talk about today anyway. So what I'll probably do is just kind of do a overview presentation with some more examples and such. I'm going to run it live on Teams and I'm going to record it. So I already have the morning class scheduled for 8 o'clock at night tomorrow. I can do yours during the day, or if you're really excited, I can do it at 9 o'clock at night tomorrow. It's going to be live on Teams, so you can join in and ask questions, stuff like that. I'll be using my good tablet computer at home so I can write and everything on it real well. Does anybody have a preference, night, day, for tomorrow? Day? Yeah, so I can run it at the same time. I can run it this time tomorrow during the day. Oh, you want a morning one, don't you? I can do morning. I can do 9 o'clock in the morning. So you guys just suck. How about 11 to 12:30?
I leave the house at 12. I mean 12:20.
Well, you missed the last 5 minutes.
Okay, if you don't mind.
No, 11 to 12 is fine with me. So 11 to 12, 20-ish. Because again, it's going to be a lot of review. We've got the major bits. We just have to kind of practice a little bit more, because I saw some people kind of struggling here and there on things. So I want to get some more practice in before we guys do the test next week. So all in all, 11 till 30. Sound good? Yeah, it's good record.
So we're not.
Yeah, you're not going to go. They'll be recording. I want to get it so that people can come if they want to ask questions, is what I want.
I can just watch it on Tuesday.
All right.
Because then you can make it easier for everyone else, not just.
Okay, show of hands. Night. Cool. Show of hands. Morning. Democracy wins. Night it is. We will do it 9 o'clock at night. I know, exciting. You guys are like, oh my God. Dr. Ireland, I'm not up at 9 o'clock at night. Huh? No. No. Online. Yeah, it's going to be on Teams. I'll send a link out to everybody. Come on. you can ask questions, all kind of stuff. Like I said, it's gonna be a final review on this material. So if you don't come, you watch the recording, right, it'll be up. The reason I can't do it Wednesday after is because I'm not gonna be able to speak. I'm getting what's called a bronchioscope, so they're, like sliding a tube down my trachea. So speaking's gonna be a little difficult on Wednesday. Might be a little hoarse on Thursday, even depending on what they hit in there, if they decide to cut things out. Yeah, I had a suspicious mass on the CT, so they're, snaking to see what it was. The good news is I get good drugs without having to crap my butt out. I can do a colonoscopy. If you're old enough to get that joke, I apologize. If you're old enough to get that joke, you are officially old. Like me. But yeah. No, trust me, that's one of those joys of middle age. Late middle age, it's one of those things you get to enjoy. But the upside is they give you good drugs afterwards and put you out. Okay, so yeah, I should be okay to talk next week. I'm worried about Wednesday, Thursday, how well I'll be able to speak, because it depends on what they do in there. If they start chopping things out, it might be a little hard to speak. So Tuesday, 9 o'clock. Not here, online, on Teams. I will send you a link. Okay? Gotta be 9, because I already got 8 to 9 scheduled for the other class. They only get an hour. You guys can have an hour and a half. Because they're my online class. So they only get an hour. Alright, so let us talk about ions. Because that's what we've been working on. And I know a lot of people have struggled with this. So, differentiating your ions, right? So we got metals. Those are going to be cations. That means those are going to be positively charged. So, if they are positively charged, do they gain or lose electrons?
Gain. Lose.
One of the two, right? Remember, protons are positively charged, electrons are negatively charged. So in order to have a positive net charge, you would have to lose electrons, right? You'd have to lose electrons. Because you can't gain or lose protons. That just doesn't work, right? So these guys are going to lose electrons. Trying to catch the board here because I want it to be more fluid and my tablet's been acting up here. So you guys got my camera. Like I said, hope the sound works out pretty well. I'm pretty loud speaker, so it should be okay. Non-metals. Obviously, if you got non-metals, so if you have metals forming cations, that means non-metals form anions, which are negatively charged. Okay? So, gain or lose electrons? Gain, right? Remember, you can only gain or lose electrons, you cannot change protons. So if I want a negative charge, I have to gain electrons. Get more electrons than I have protons in the system. Proton number is never, ever, ever, ever going to change, right? In order to do that, you need radioactivity, which we ain't doing. It's kind of fun, but we're not doing it. Okay, so what about the metalloids, Dr. Allen? We're not talking about the metalloids. Redhead stepchildren of periodic. They've got all kinds of weird properties, and depends on the mood they're in as to what they act like. We'll talk about a little bit in covalent bonding. We're not going to talk about it here. Now, we got to differentiate between type 1 and type 2 ions. Okay? So, type 1, only one possible charge. Okay? Only one possible charge in a type 1 ion. That is groups 1 and 2. Alright? So group 1 and 2, so alkali metals and alkaline earth metals. All nonmetals. And then we have special case for aluminum, cadmium, right? Zinc, right? Zinc, and silver. All right? So, those are all the type 1 ions. Again, not discussing metalloids. All right, type 2. Type 2. Multiple possible charges. I want to make sure I don't go too low. Multiple possible charges, and this is all non-type 1 metals. All right? So that is the vast majority of the metals, right? Type 1s are group 1, group 2, aluminum, zinc, cadmium, and silver. Those are the only type 1 metals. Every other metal up there. Transition metals, post-transition metals, inter-transition metals, all of those are type 2 ions, meaning they have more than one possible charge. Okay? So when we're talking about elements, we have to distinguish whether we're talking about a type 1 or a type 2 ion. Now, let's talk about the naming of these. Okay? So, type 1 metals. Type 1 metals is simply the element name followed by ion. So an example of this, right? An example would be silver ion, right? So all type 1 metals are just simply element name followed by ion if you try and name the ion, okay? So, we don't have to say type 1 nonmetals because all nonmetals are type 1 nonmetals. We'll say type 2 metals. Now, for this, you need the element followed by, in parentheses, the charge, and that's going to be in Roman numerals. Ion. So, this guy here is in Roman numerals. Believe it or not, I actually like doing it on the board rather than PowerPoint. I enjoy it more. Kind of feel it. I wish there was a chalkboard though. Really miss chalkboards. Okay, so element name, charge, ion. So what's an example of this? So example of this would be something like iron to ion, which would represent Fe2+, right? You got the element name, the charge, which is 2, Roman numerals, not 11, right? Which is 2, so that tells you it's an iron 2+ ion. So that would be how we name type 2 metals. All right. You guys got this? All right. All right. So the last one would be the nonmetals. Sorry, I got a little hay fever going, so you hear me sniffle. Non-metal ions. It is going to be the element name in the "-ide" form, followed by, just putting that there because I'm talking about it, ion. So how's this look? Well, there's only a few of them, right? So C becomes carbide, N becomes nitride, and you don't have to capitalize them, I'm just doing it. Oxide, fluoride. Not really doing these in good order. Sulfide. Should have done phosphide first. Phosphide. Chloride. Bromide. Iodide. The last one would be selenide. We're not going to put acetine on there because, again, it's the bottom of the thing. It's radioactive. Don't give a crap about it. So these are the only "-ide" forms you have to worry about. You notice it kind of chops off the last syllable and puts "-ide" on it, right? So if you want to name a non-metal ion, you can use this "-ide" form. Phosphide. Technically, you could also use hydrogen. It's hydride, but that's a less common form of hydrogen. Typically, hydrogen is a positively charged ion, so it'd be the hydrogen ion. So hydrogen is kind of unique because it has two names. It's positive, it's hydrogen ion, and it's negative, it's hydride ion, but hydride's less common than hydrogen. All right, so we're on the same page on how to name stuff. At least got it written down so we can refer to it in a minute when I ask you to do stuff. Good. Right there, Dr. Ireland. Makes complete sense. Nomenclature is one of those things you either get it or you don't. And if you don't, you just have to practice a lot. Because everybody can get it. It just takes time. All right. We good? You did it. I'm recording it too. I don't know how it's going to come out in the recording, but I got it on full HD. I didn't want to put it on Ultra HD because I can't take that long. All right, got it? Last call. All right. Whee! Go really old school and set up my camcorder in the back. I think I'll find a firewire cable to transfer things. I don't know if we make those anymore. Okay, next up. How do we know charges? Right? How do we determine the charges on things? Some of them are easily predictable. All right? So our predictable charges. We've gone over this stuff before. That's what I'm not getting into new stuff yet. This is the stuff we've done before, but some people seem to be a little fuzzy on it last time, so I wanted to go over it again. So, predictable charges for ions. Group 1 always equals positive charge. One positive charge. No, not putting a 1 in there. Group 2 always equals 2 plus charge. And if you're in biology, they go plus plus. Bio people. I had a talk with Brian about that. I had a meeting, he was sitting next to me at the meeting on Friday. I said, so, Brian, how do you write a calcium ion? God damn it. He goes, I've already heard this from your students. It's like, I didn't write the Quizlet. I was like, if you had iron 5, what would you write? Iron plus, 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 plus. You guys know that'd be stupid. Yeah, I kind of like plus pluses. But yeah, biology people are going to do that. I don't know why. All right. So those are metals. Aluminum always equals 3 plus. Zinc and cadmium always are 2 plus. And silver is always plus. All right? So that takes care of all of our type 1 metals. Right? So remember, type 1 metals, group 2, or group 1, group 2, and then aluminum, zinc, cadmium, and silver. Aluminum actually makes a lot of sense because if you eliminate the transition metals and you go straight across, it'd be 1, 2, 3. Right? Now, what about the non-metals? Right? Don't worry, it's not too bad. Non-metals are actually pretty straightforward. Okay, so non-metals. Non-metals. So we're going to ignore group 13. We'll come back to group 14. So group 14 is only carbon. All right? And in a pinch, you'll get 4 plus for the carbide ion. Like I said, doesn't really like doing ionic bonding. It can. You can make it do it. And there's lots of common does not start with a P. It starts with C. Alright. So you got a pitch can make it become 4 plus. Okay. Group 15. That's going to be nitrogen and phosphorus. So nitride and phosphide. Now why is it 3? Well, remember, what ions are trying to do is they're trying to become stable. They are trying to look isoelectronic. Remember that fancy word? My mom used to call it a 50-cent word. Isoelectronic means the same electron configuration as a noble gas. So the nonmetals are adding electrons. Why did I put plus? Why? Okay, bigger question. Why didn't anybody question me on it? Because you know what you're doing, Dr. Adam. You know. Apparently I don't either. Negative. Anions. Remember that, anions. Oxide, sulfide, and selenide. All right, group 16, all 2 minus for the nonmetals. Why? Because they're trying to add electrons to move forward to the noble gas in front of them. All right? Oxygen needs to add 2 electrons to look like neon. Right? Sulfur needs to add 2 electrons to look like argon. Selenide needs 2 to look like krypton. The element, not the planet. Right? I honestly don't know which was named first. I think the element was named first. Interesting question. All right. Group 17, the halogens. These are all 1 minus. Again, not putting an sign on there. So these only need 1 electron to move forward to that noble gas. In contrast, these guys are losing electrons to go to the previous noble gas, right? So lithium is 1 plus because it loses electron, looks like helium. Potassium is 1 plus because it loses electron, it looks like argon. Group 2s, they lose 2 electrons, they look like the previous gas. Aluminum, same idea. These guys, why are these guys this then, Dr. Arlen? Because very complex theory why. You memorize it because you don't want to understand the quantum mechanics as to why this happens, right? Has to do with relativity, actually, in some cases. There is a theoretical limit to how big an element can be, because at a certain point, outer electrons would have to move faster than the speed of light. So, can't do that. And you're pushing it down to the bottom. Okay, so, these are all of our type 1 elements. Again, excluding metals. These are our type 1 elements. These are the only ones that have that single charge. So these are the metals that you can just say aluminum ion, silver ion, calcium ion. Do 2+, don't do that stupid stuff. Alright? Lithium ion. Over here, these are the ones we talked about. Nitride, sulfide, phosphide, bromide, right? Only one possible charge. So this is type 1. By the way, for those who came in late, recording video, little red lines are how far I can see on the video. That's why they're there. Alright, we got this? You cool with this? Okie dokie. So, I like boards. I like the eraser actually works. Sometimes it doesn't work too good if you get those low odor markers. These are actually fancy. We can replace a cartridge in them, so you don't have to throw them away. All right, type 2 ions. All right, so type 2 nomenclature. Type 2 ions. What are we looking at? Well, we have to know the charge. We have to know the charge on it because ionic nomenclature is always about having one and only one possible name to each formula, right? When I write a formula unit up there and I give it a name, it has to be completely unambiguous. Reading that name has to give you only one option, okay? Now the problem with type 2 ions is there's more than one possibility, right? So if I say iron, that's not good enough. Because what iron are we talking about? So how do we know? Well, we're either told, right? Someone says, hey, it's iron 2, or it's iron 3, or iron 4. Or we figure it out from the formula, right? So a formula unit is the 2 ions together, positive, negative. Don't knock my camera over. It's the problem you guys sit there and try and do this. So, how do we use a formula to figure out the name? Well, let's do easy examples. Let's do that one. All right? Now, how do we know what the iron's charge is? Well, we know it because of the anion, because of the negative ion. Because remember, all the anions we're going to work with are type 1. They only have one possible charge. So as I'm going down this, the oxide is exactly the same charge in each case, right? So this is 2 minus times 1, right? Which gives a total charge of 2 minus. This is 2 minus times 1, which gives us a 2 minus charge. This one is 2 minus times 3, which gives us a 6 minus charge. And this one is 2 minus times 2, which gives us a 4 minus charge, right? Each of the oxides is 2 minus. Now we use the number for each of them to get the total negative charge in the system. Follow me so far?
No.
Each oxygen ion always has a 2 minus charge. Oxygen's type 1, always 2 minus. to get the total negative charge in each of these compounds, I take 2 minus and multiply it by the number of them I have, right? So 2 minus times 1 is just 2 minus. 2 minus times 3 would be 6 minus. 2 minus times 2 would be 4 minus. Follow me now? Crystal clear as muddy water?
It's just, because the FE is, I guess.
We haven't talked about the FE yet.
We're just talking about the O.
We're just talking about the O right
The
now.
O always has minus 2
Yeah,
charge.
we're just talking about
You just
total
multiply
negative
it
charge.
by how many you have.
Okay.
Right? We're just talking about the oxygen right now. So total negative charge. That allows us to determine the charge of the iron. Because we know that the positive charge has to be equal to the negative charge. Right? So we know, in each of these cases, we know that I need 2 plus here, 2 plus there, 6 plus there, and 4 plus there, right? Because I have to have the opposing charge for each of them, right? So it's 2 minus, it's got to be 2 plus. Now, the way I figure out the charge on the iron is I take that positive charge I have to have, and I divide it by the number of irons I have. So in this first case, I would take that 2 plus charge, and I divide it by 2, because there's 2 irons up there. Follow me? So that means my iron is 1 plus. I'm putting the 1 up there just so you see it. Right? Next one, 2 plus divided by 1. That means it's 2 plus. Now we get down here on iron. I have 6 plus. I'm going to divide it by 2. That gives me 3 plus. And then last but not least, 4 plus divided by 1 gives me 4 plus. So this is the charge on the iron. That's the charge on the iron. Now we can write the names for this. Right? So remember, in type 1 elements, all you do is just write what you got, right? Sodium chloride. Yeah.
Sorry, I have a question.
Yeah.
How did you get the numbers that you divided by? So like 2 plus divided by 2?
The number of the irons present in the formula. Everybody see that?
So you'll always take what you get and just make it positive. And then
Well, yeah, because
combine-
you have to be the opposite of this charge, right? For it to be electrically neutral, if I have a 4 negative charge, I gotta have a 4 positive charge. Because remember, the goal here is to get a compound that is electrically neutral, a formula unit, smallest formula unit, that is electrically neutral. So my oxygens tell me my negative charge, my cation has to be the opposite of that. So I take the total charge that I need, right, which I get from the oxygen, and then I divide it by the number of irons I have in the system. Doing good? Again, crystal clear as muddy water.
So the name for that?
Next up.
Don't jump on it.
Yes, we're going to talk about that. How do we name them? All right? We name them based on these values. Okay? Because these are the charges of the individual iron ions. Right? So this first one here, we would name iron 1 oxide. Because looking over there, it is a 1 plus charge. So, iron 1 oxide. The next guy we would name iron 2 oxide. No, the only thing that's going to change in these names is that Roman numeral. Right? Is that Roman numeral. Because the Roman numeral is the charge on the ion. Okay? Next one. Iron 3 oxide. And last one. Iron 4 oxide. That's Roman numeral for 4. Iron minerals. Old dead white dudes from Europe. That's why. Whenever you ask why we do something stupid in here, old dead white dudes from Europe. Okay. So everybody see how I got these? Number one mistake I see. I always try to tell students the simple mistakes I see throughout the exams and stuff. Number one mistake I see. People confuse this with the number of them they have. Right? This is not the number of them you have, it is the charge on the individual cations. Make sense? I'll make it harder in a second. I'm just gonna have you name things.
So in what case,
Yes.
what case would we use, okay, so to name type 1,
Yep.
you would just,
Yeah, so I'm gonna erase it from over here.
Can we do another example before you?
Yeah, we're gonna do a lot of it. I'm not gonna do one example and be done.
it's just the name and ion.
Right,
all
so
type
type 1, right? So type 1, we say that, right? That's a type 1 ionic compound. Both of those are type 1 elements, right?
Okay.
Because sodium is
Mhm.
group 1, oxygen is a non-metal, all non-metals are type 1, right? Now, you're like, oh, do I have to say di? No. All you have to do in ionic compounds is name the ions in the system, right? So if I look at this, I would say it is sodium oxide. Because remember, that's got to be changed to I form, we talked about a minute ago, right? But since there's one and only one possible charge on both the components,
It's just sodium.
it's sodium oxide. Because you know, by nature, this is 1 plus, this is 2 minus, therefore the only way it works is to have 2 sodiums per 1 oxygen, right? So we can't come up with another formula for this other than Na2O. That's the only possible formula you would get from the system. So we meet our criteria. 1 formula for 1 name, right? Don't worry, I'm gonna do more examples.
No, I guess I'm just like, maybe it's just not clicking in my head, but where do you get the 1 and -2? That's from the type?
Sodium is a group 1 element, right?
Yeah.
Group 1 elements have 1 and only 1 charge. Group 1 elements are always 1 plus. Because they are in the far side of the periodic table. If they lose 1 electron, they look like the noble gas that came before them, right? So if you look over there, you see sodium. Sorry, I don't have the camera going that far, right? You see sodium. If you take 1 electron away from sodium, it looks like neon. Therefore, 1 electron away is stable. So you get a 1 plus for sodium. Oxygen, over here on the periodic table, group 16. For it to look like neon, it has to add 2 electrons, right? Because it has 16 to start, or 8 to start. I add to it 2, that gets me to 10. And that's where I want to be. I want to be at a noble gas, right? So 2 electrons means it's going to be 2 minus. So both of these are type 1. They only have 1 possible charge. In contrast to that, right? Type 2, multiple possible charges. So you have to state which charge you have. You're doing the same thing in both cases. You're simply naming the ions in the system, right? Sodium oxide. I'm doing the same thing over here, right? When I say iron 2 oxide, I'm saying, hey, I've got Fe 2 plus, and I have O2 minus, right? Because oxide is always 2 minus. Remember, all nonmetals, 1 and only 1 charge. I've told you what the iron's charge is. in the name. So if I combine these two together in the lowest whole number ratio that gives me 0, I get that. Fe2 plus, O2 minus, 0. Want to try some more examples? Like, no, Dr. Early, no, you're not. But you're going to make this? Yes, I am.
Wait, so that is type one.
Yes.
And not size.
That's it. Alright, so let's do some examples, because like I said, if it doesn't click, the only way it clicks is through multiple examples.
So where's iron on there?
Don't worry. You lose the term ion when you combine them together.
No, I'm just trying to connect the periodic table to this. You said it's in group 2.
I'm gonna be off the screen here. So,
Group 1.
group 1, lose 1 electron, and you look at that, right? Because I have 19 electrons here in potassium. Take 1 away. How many do I have?
18.
Right? Looks like that. Barium. Barium has 56 electrons. Take 2 of them away, and I end up looking like xenon, which is stable. On the other side of the periodic table, phosphorus. If I add 3 to it, I look like argon. Stable. Right? If I added 4 to it, I'd be over here. That wouldn't be stable. Right? If I took 2 away from here, I'd be here. That wouldn't be stable. Right? I want to land on the noble gas when I form ions. Yeah.
Is that why the colors are red, the names are red and black? Because it's
No, that actually deals with the state of them at room temperature. So if things are black,
Because only row 18 is
yes, they're all gases. So red indicates gas at room temperature, blue indicates liquid at room temperature, and black indicates solid at room temperature. That's kind of debatable. You need to be about 80 degrees for that to melt, but we'll give it to them. It's close to room temperature. It's room temperature in this room. Room temperature in the office, good God. Now, you put it out in there, and definitely melting. Okay. You're leaving already?
Yeah, I looked way there, and they said I have to pay them like.
That's what I'm taking. You can watch it later.
Okay.
All right. So, let's do some examples, because like I said, only way this works is if you do examples. You just stare at me all day, it doesn't help. I know I'm pretty, you don't need to stare at me. All right. Let's have some fun. I know, very weird version of fun, Dr. Arnold.
Well, okay, so now I understand why you're saying where's iron on the.
Yeah, that's what I'm saying.
So why does iron only get 1 charge? Yes.
Yeah, now I mean.
Well, iron does not have only 1 charge, it has multiple charges.
So how do you
Like I said, the only metals that have a single charge
or type 1?
are type 1s, which is group 1, group 2, and then aluminum, zinc, cadmium, and silver. Those are the only metals that are type 1. All the rest of them, type 2.
So pretty much what you're saying is you,
Give me a second. Let's try some examples.
okay, alright.
Try some examples. So we're going to do name to formula, formula to name. Okay? So we're going to say Okay, so 4 names of compounds. We're going to try to figure out the formula unit for each of these names. Okay? So when you're trying to figure out the formula unit for a name, you have to figure out what ions you have, right? You need to know what the ion is and what the charge on the ion is. Dead giveaway you have type 1 elements is there's no parenthetical statement on them, right? So this one and this one are type 1 only. Now who remembers what the charge of aluminum is? No. 3 plus. Way to remember it. Sodium 1 plus. Magnesium 2 plus. Aluminum 3 plus. Because remember, these aren't in there yet. Right? In period 2, you're just going 1, 2, 3. Right? So aluminum is 3 plus. What's chloride? 1 minus, right? Because it's in group 17. Group 17 is right before the noble gases, so if I give them 1 electron, they look like the thing in front of them. Okay, now, I have my ions. Now I have to get the lowest whole number ratio that gives me a net charge of 0. What's that going to be? I want the lowest whole number ratio of the aluminum and the chloride ion that will give me a net charge of 0. Exactly. AlCl3. Because Al's 3 plus, chloride's 1 minus. So if I have 3 chlorides, I have a total charge of 3 minus. Right? So 1 aluminum, 3 chlorides gives me a charge of 0. Right? Because this, right? This is 3 plus. This is, I'm going to put the 1 in there. 1 minus times 3, so 3 minus. Right? So I take the charge on the individual chloride, multiply by how many I have. Right, let's try another one. What is the charge on my vanadium? 3 plus, good job. What's the charge on my nitride? 3 minus. And you're like, why'd you get those things, Dr. Ireland? We know that vanadium's 3 plus, good, got to run number 3 after it. Right? Means it's 3 plus. Why is the nitride 3 minus? Well, nitride is in group 15. Remember, we're trying to get to group 18. So if I want to get to group 18, I have to add 1, 2, 3 electrons to it. Right? I'm at 7, I want to be at 10, that's 3 extra electrons, hence 3 minus charge. Alright? Somebody from this side of the room, what do you think the formula unit is? On this side. Take a stab at it. Worst thing you can say is wrong. Exactly. Vn. Vanadium's 3 plus, nitride's 3 minus, 3 plus 3 minus equals 0. Sometimes they're that easy. Okay. Potassium. What's the charge on potassium? 1. Good job. What's the charge on phosphide? 3 minus. And if you're like, again, Dr. Ireland, please explain. Potassium, number 19. Take 1 electron away from it, looks like argon. So, minus 1 electron, plus. Phosphide, right under nitrogen. Acts exactly the same. I need to add 1, 2, 3 electrons to get to argon. So 3 minus. All right. We'll go in the middle row this time. Column, sorry, middle column. So you 4 guys, one of you has to answer this. What's the formula for potassium phosphide?
KP3. K3P.
There you go. Why? Because that's 3 minus, that's 1 plus, so I'm gonna need 3 of those to equal 3 plus, which cancels out that. Does that make sense? So you get K3P. All right, last guy down here. What's the charge of chromium?
4.
4 plus. IV. Not III. IV. Grand scheme of Roman numerals, which are stupid. You guys are all young enough, you didn't have to do the thing where you learned Roman numerals and Egyptian numerals and all that kind of crap when you were in elementary school. That was one of those things they did when I was a kid. I don't know why I had to learn them, but I can now tell you 2002 in Roman numerals. Alright, so chromium is 4. What is the charge on oxygen? 2 minus. Good job, guys. Okay. This column, very good. CrO2. 2 minus, 4 plus. I'm going to need 2 of these to get to 4 minus, which cancels out that. So 1 Cr, 2 oxygens. Starting to kind of make sense? You're like, sure, Dr. Ireland, until you do the next thing, which is we're going to take formulas and turn them into names. Okay? So let's go with okay. So we got 4 ionic formulas. Alright? First thing we want to do in each of these is look at the metals. Identify whether the metal is type 1 or type 2. Right? So as we go down through here, we look at the metal. Calcium. Okay? Calcium is in group 2. So is it type 1 or type 2? 1, right? Always has a 2 plus charge. Do we need to worry about the charge right now? No, because type 1 elements always give you just the names of the stuff. Alright? Calcium ion, oxide ion. If I say calcium oxide, it only equals that formula. Because calcium is always 2 plus, oxide is always 2 minus, so CaO. Next up, cobalt, type 1 or type 2? Cobalt is right here. Type 2. CO is cobalt, Cu is copper. Alright? So, type 2. Alright, so what do I need to know? What kind of charge it has? How do I determine what kind of charge it has? I look at the anion. Chloride. What charge does chloride have? Say it loud, say it proud.
2 minus?
Nope.
1 minus.
1 minus. Anion. Non-metals are anions. Don't worry, I screwed up early. Alright, so 1 minus. Group 17. Move 1 forward. Okay? So, if we know that chloride is 1 minus, what does the charge on cobalt have to be? 2 plus, right? Because I got 2 of these, which gives me 2 minus. I have 1 of those, so it's got to be 2 plus. So I know this formula is, or this name is cobalt 2 possibility for that name to turn into a formula, right? 2 plus on cobalt, 1 minus on chloride, so I get CoCl2. All right. Down here, barium, type 1 or type 2? 1. It's in group 2. It's in group 2, but it's type 1, right? Because all of group 2, always 2 plus. All right. If it's type 1, what's the name of that? Barium chloride. Doesn't need anything else. One and only one possibility. Okie dokie. Last guy. Cadmium, type 1 or type 2?
2.
How many people say 1? How many people say 2? How many people say I have no freaking clue?
Both.
There you go. It is type 1. 4 group, right? 4 of them. 3 plus. What are these 2? 3 plus, 2 plus, 1 plus. 3, 2, 1. So cadmium, always 2 plus. So when I write over there, all I gotta do is say, hey, this is screw you. Cadmium oxide. Okay? So, we're going to stop with this for a moment. So we're moving to covalent. We're going to come back to this at the end. So we need to talk about covalent first. Okay? Because the last thing we're going to do with this involves covalence. Okie dokie. My wife makes fun of me because I say okie dokie all the time. I have for years. Then we started watching the Fallout series on Prime. The lady on there keeps saying okie dokie. She's one of those things I picked up somewhere.
Are you already caught up on it?
No, I have not finished the season. I've seen like bits and pieces online, but I haven't seen this season.
They're still releasing every Wednesday and that's what drives.
My wife is a reality show freak, so she's been watching Traders. It's not her Hallmark movies with her. I'll watch the reality shows. Alright, so let's talk about covalency. That is not how you spell that, right? Covalent bonds. Now, when you look in a book and you're reading the book, they're going to use the same phrase every time. Covalent bonds is the sharing of electron between 2 atoms. Okay? Makes it sound all kumbaya. You have them for a moment. No, you have them for a moment. Let's just share them together. It's kind of more like when my kids were younger and I told them to share the TV. As long as both of them had one hand on the remote, that was sharing, right? Because this is what happens. Both of the atoms in a covalent bond are trying to pull the electrons towards themselves, right? In an ionic bond, this happens. One of them says, screw it, I don't need it, you take it. And the other guy's like, cool, takes it. Positive, negative charge, smack together. Here, you got 2 atoms going, I want the damn electron. And the other one's like, so do I. And so they both put a hand on it and pull. But neither of them has the ability to yank it away from the other. So it just kind of sits there in the middle, right? Forming a connection between the 2. And this is a very different type of bond because an ionic bond is only held together by electrostatic interactions, right? The positive and the negative charge interacting with each other to cancel each other out. A covalent bond is a physical connection between the 2 atoms. And you're like, well, what's the difference, Dr. Arlen? You ever play with magnets when you were a kid? Right? You know, you take north, south pole magnet, they'll click together. And if you got strong enough magnets, You can put something between them and they'll still click together, right? Because the positive and the north and the south will attract to each other, even through something. As long as there's a strong enough magnetic field, they'll yank together. And that's the key. What's holding together an ionic system is just this network of positive and negative charges attracted to each other. They are not physically connected to each other, they're just held together by this electrostatic force. In covalent compounds, you don't have that. You've got two things that are intimately tied to each other. Because they're taking a pair of electrons and trying to hold them with each other. So the best way to describe covalent compounds is using something called Lewis structures. Now, any of you guys read part of the chapter about Lewis structures? You're like, read? What's that, Dr. Ireland? Aren't you going to tell us everything we're supposed to know? Not always. That's why I assigned reading. Yes. So let's talk about Lewis structures. So, Lewis was a famous American chemist in the early 1900s. Probably either one or two most important chemists in the United States, come out of the United States, right? It's him and a guy named Linus Pauling that kind of run neck and neck for the most important American chemist. Which is funny because both of their major works involve covalent bonding, right? So, what did Lewis say? Well, Lewis was trying to describe a pattern he saw in bonding. Lewis is before modern quantum mechanics. It's kind of like right before it, where they're trying to describe things classically rather than doing all the funky math for quantum mechanics. Right? I did the math once. I did it on a computer and it still sucked. I can't imagine people who did it by hand. Whew. That's some brain power I don't have. So Lewis gets this idea, he starts looking at the period 2 elements. Right? So if we look at period 2 elements, we have lithium, beryllium, boron, nitrogen, oxygen. No, iron does not jump into group 17, Dr. Iron. Fluorine, and neon. All right? Those are period 2. Those are period 2. I agree with that, right?
No, what's period 2?
Row 2. Rows are periods, columns are groups. Right? So there's 18 groups, 7 periods. So, he looks at this and he says, all right, we know we have this concept of valence and core electrons, right? So we can look at any atom and we can describe it in terms of how many core and how many valence electrons it has. And when we're doing chemistry, the only thing that matters are the valence electrons. So, how do we determine how many valence electrons are in period 2?
We subtract the number of...
You're there, come on.
electrons
In
from the atomic...
It's almost there. Come on, you do it.
I know it, but I don't know it. I do it.
I know it's somewhere in my notes. Somebody want to give her an assist? Subtract the number of electrons in.
Atomic number? No.
Which atomic number?
Atomic mass?
Nope.
No.
All right. I'll give you the layup.
Alright.
You got close. You got most of the way there. You do subtract the number of electrons. The number of electrons you subtract is the previous noble gas. Because remember, the electrons that end in noble gas, those are stable, right? So if I'm looking anything in period 2, I've got to subtract 2 electrons. Because those 2 electrons are core. Right? Those 2 electrons are core. So every one of these guys, right? Every one of these guys up here has core electrons of 2, 2, 2, 2, 2, 2, 2. All right? Those electrons are not going to do chemistry. Core electrons do not do chemistry. Unless, as I always say in chemistry, you can do anything if you use enough energy, right? So technically you can get it to work, but that's going to take a tremendous amount of energy. Way more than you're practically going to use. All right. So if we know there are 2 core electrons for each of these, the rest are valence electrons. So how many valence electrons does lithium have? Well, how many electrons does lithium have? 3. So if I got 2 core, how many valence do I have? 1. Okay, beryllium, how many would I have? Minus
Well, let's figure out
2.
that.
2. And then 3, 4, 5, 6.
Did we count carbon?
Oh, I forgot carbon. That's why this messed up. Carbon. See, the guys need to tell me one of this. I was about to get it. I was about to get it too, because I saw that and I saw 7. I said, I screwed up somewhere. I was too excited to get to neon. Carbon, nitrogen, oxygen, fluorine, neon. Sorry about that. What's really hilarious is I'm an organic chemist. All we do is deal with carbon. I forgot the little boy. My favorite little element. I forgot him. Alright, so now with the advanced tool. Valence electrons, 1 through 8. Right? Once you get the neon, stable. So, Lewis had one more thing he looked at. One more thing he looked at. Last thing he looked at is maximum bonding. Now, in particular, he was looking at the maximum number of covalent bonds formed. Right? Covalent bonds formed. Not ionic, covalent. Okay? So, lithium, non-issue. Doesn't form covalent bonds, don't give a crap about it. Right? We can explain ionic bonding with Lewis structures, but we're more interested in explaining covalent bonding. Right? Beryllium is a metal. And you're like, well, beryllium is a metal, Dr. Allen. You can't form covalent bonds. Beryllium is the only metal that can form covalent bonds. Right? It's a little weird. And it can form a maximum of 2. Boron, metalloid. It can form covalent bonds. It can form a maximum of 3. Carbon can form a maximum of 4. You're like, neon, or nitrogen, 5. Nope.
Goes down.
3. Oxygen, 2. Fluorine, 1. Neon, 0. So he's taking all this data and he's like, okay, how can I combine all this data into something that is useful, right? That explains this, right? How can I explain the idea that valence numbers go up the entire way across the period, the maximum number of bonds doesn't? It goes up, then it goes down. And Lewis develops what's called the Lewis structures. All right? What are Lewis structures? Lewis structures are a graphical way of representing the valence electrons that account for that bottom row, maximum bonding. So the way the Lewis structures work is you put the valence electrons in around the symbol for the element as dots. Now, lithium, doesn't matter where you put it. Most people start at the top, north. And you're going to put them in the cardinal positions, north, south, east, west, right? So, beryllium, 2. All right. Boron, 1, 2, 3. Carbon, 1, 2, 3, 4. All right. Now comes the insight that Lewis had that really got him kind of going. Because, this stuff is exciting. Lewis said, all right, this kind of makes sense. Beryllium bonds twice, so a covalent bond is a sharing of a pair of electrons. So if this bonds twice, this brings in one, something else brings in one, you get 2 bonds. Boron, 3 of them, 3 bonds. Carbon, 4 of them, 4 bonds. Nitrogen, 5 electrons, 3 bonds. So he says, okay, what happens is you start pairing them up. So nitrogen gets 3 singlets and 1 doublet. All right? And what Lewis says is this explains the bonding because you have 3 single electrons available to bond, right? They can form part of a pair with somebody else. And then you have this guy. These are 2 electrons. You can't shove another one in there to cause a bond. So these 2 are what are called an unshared pair or a lone pair, depends on who you want to talk about. So depending on who you're asking, and the book even has a little bit of a confusion about it because it uses 2 different names for them. Or non-bonding pair. Any of these 3 can be used. The book has a confusion with itself because it uses the term unshared pair and lone pair in 2 different positions in the book. They mean the same thing. Non-bonding pair, or sometimes you'll see that. I don't know what they use in biology. I'm gonna guess unshared pair, but don't quote me on that. Ask Brian, he'll tell you. What we'll probably say is, we don't bother with that. All right, so, oxygen. Keep with the pattern. 2 pairs of doublets, 2 singlets. So, 2 unshared pairs, 2 bonding electrons. All right? Go over to fluorine. You get 3 unshared pairs and 1 bonding electron. Then finally over here on neon, where you got 8 valence electrons, you get 8 into 4 unshared pairs. And since none of these are singlets, nothing can bond to it. Hence it is stable. Right?
Wasn't it that means the octet?
Bingo! This is where he develops what's called the octet rule. The octet rule says that covalent bonds are trying to reach the point that everybody in the system has a complete octet. A complete octet. Now, I always joke with my students in organic chemistry. I said Lewis's idea is completely and totally correct down through the end of period 2. Once you get to period 3, some weirdness happens. And you're like, and what's the frickin' point if you can only go through period 2? And I tell my organic chemistry students, the amount of times you will go below period 2 in organic chemistry is very, very limited. Most organic chemistry involves the elements in period 1 and period 2. Everything else, kind of. Right? So, everything through period 2 absolutely follows the octet rule. Noble gases always follow the octet rule. Halogens actually always follow the octet rule. Other than that, there's some weirdness that goes on. All right? But this allowed, like I said, this allowed Lewis to describe what a covalent bond was. If you were talking about, say, water, which is H2O, in case you didn't remember, right? Then he said, oh, well, the way it works, right, is you have the 6 valence electrons from oxygen, and then each of the hydrogens gives you 1. So now I have 8 around the oxygen, and I have 2 around each of the hydrogens. And you go, that's not 8, Dr. Ireland. The octet for period 1 is 2, right? Because the noble gas there is 2, right? So hydrogen has to get to 2. All right? So this allowed Lewis to describe what covalent bonding was. All right? This was the first true explanation of what a covalent bond was. And it held for quite a bit of time. It held until the, I want to say 50s, I don't remember exactly, when Linus Pauling took this, went with it, and turned it into quantum mechanics. Right? And then gave a quantum mechanics explanation for what a covalent bond was. He won the Nobel Prize for this. Lewis did not. Lewis was nominated, I think, 40 times for the Nobel Prize. Because he not only did covalent bonding, he also described acid base. He did a bunch of stuff, a ton of stuff. But he happened to be active at the point in history where the Nobel Committee, which you know is European, the Nobel Committee thought that Americans were just a bunch of young cowboys still, and didn't think any of them deserved the Nobel Prize. So he was repeatedly nominated and repeatedly shot down by the European Committee. So never won one. There is a thought it got to him over time because he died in a lab accident that he should have known would have occurred. So there is a thought he might have unalived himself in the lab because he had talked to one of his mentees the day before and apparently seemed very depressed. So a lot of Nobel Prizes. To his credit, almost all of his significant students won Nobel Prizes. Right? So he was a great mentor. All right, so now that we know what a covalent bond is, this sharing of electrons, let's talk about how we name covalent compounds. Because why not? Covalent compounds are always fun to name. Okie dokie. I say okie dokie a lot and I say y'all a lot. I blame the y'all on 5 years in North Carolina grad school. Although I have 2 nieces that are from Alabama and they tell me I pronounce y'all incorrectly. Apparently there's an Alabama way to say it and a North Carolina way to say it. So, naming covalent compounds. Naming covalent compounds involves a foreign language, but it's not Latin. It's Greek. So let's have some fun. So what we need to know are the Greek prefixes for numbers. And you're like, what? All right, Greek prefixes for numbers. And before you guys go, oh my God, why do I have to remember this many? My organic students have to know through 20, so you're getting off easy. All right, most of these you actually know. Mono equals 1, di equals 2, tri equals 3. The ones that will throw you are tetra, which is 4. Penta, which is 5. Hexa is 6. Another one you won't know, hepta, which is 7. Octa, 8. Nona, 9. And deca, which is 10. All right? Hi-ho. 1 through 10. To be honest, probably won't use 9 and 10 much, but I'll put it up there anyway. These are the Greek prefixes for numbers. And since I said the word prefix, you kind of know how this stuff's going to be used. All right? So, the rules for naming. For you guys, we're just going to go name left to right. We are going to be looking at what are called bivalent compounds. What it means is they're made up of 2 elements. They might have more than one of each element, but they're only made of 2 elements. All right? So you're just going to name them left to right. And when you're converting the name into a formula, you're going to write the formula left to right in the name. Okay? Nice and easy. Not going to make it real complicated for you. Go with the easy ones. use the prefix for the number of each element. You're like, sweet, this makes total sense, Dr. O. I'm ready to go. With the following exceptions. Exception 1. Do not use mono on the first element. Alright? So, you guys actually know this one. You guys know the term carbon dioxide, right? And if you know the formula, you know it's CO2. So there's one carbon. We don't call it monocarbon dioxide, we just call it carbon dioxide. So if the first element only has one, you leave off the mono. Alright? Second exception. If you have I'm gonna move this one. It's going too far down. I'll move it over here. B. 2B. If you have a prefix ending in A or E, in front of oxygen, the vowel. Why can I spell vowel? V-O-W-E-L? Okay. For some reason my brain farted on that one. And again, you know this one. Carbon monoxide, right? Carbon monoxide is not carbon monoxide. It is carbon monoxide. Oh, I forgot the O, sorry. Forgot the O. A, E, or O. A, E, or O. So, the last rule. Those are two exceptions. Number 3. The second element ide form. So the second element's written in the ide form. So, second element's written in the ide form. So again, carbon dioxide, right? Carbon monoxide, right? Hydrogen sulfide. Alright, so the second element's in the ide form. This is one of the dumbest rules from the old dead whiteys in Europe, in my opinion. Because you use the same form in both ionic and covalent bonds. Don't they come up with something different between two? Make it easier to remember the difference? No, it's the same thing. Alright? So, the examples. That'd be cramped. You guys got the prefixes? So I can recite. Alright. Need a wider lens so I get the whole board. I should bring my camera in a wide angle lens. It does the deal. I don't think it does an hour and a half though. Alright. So, let's look at N4P5. Now the first mistake students make with this, Alright? The first mistake students make with this is they start thinking in terms of charges. Like, oh, nitrogen's 3 minus, phosphorus 3 minus, what the hell is going on, Dr. Ireland? You got a lot of minuses in there. And the answer is, it's covalent. There are not charges. All you're doing is naming what you got up there, right?
Oh my gosh.
So I have 4 nitrogens. What's the prefix for 4? Tetra. So I would call this tetranitrogen pentaphosphide. Alright. Prefix for each of them. Tetra and penta, representing the 4 and the 5. First element's just the name, so nitrogen. Second element's in its ide form, so phosphide. Tetranitrogen pentaphosphide. Alright? Let's do another example. Let's go with alright. So, how to name that? Phosphorus. And if you're like, but Dr. Ireland, there's one of them.
Phosphorus dioxide.
Phosphorus dioxide. Phosphorus dioxide, right? We don't put the mono in phosphorus, rule 2A there, right? It's mono in the first one, we don't put it in. Second one, 2 of them, but it's not A, E, or O, so we keep the dioxide. Right? Now, let's go for some fun stuff. All right, first one, sulfur. Second one,
Tetroxide.
tetroxide. Note, drop the A at the end to B, right? So it's going to be tetroxide. You lose the O or the A, so it becomes tetroxide. Now, if you're like, why do you do that, Dr. Ireland? It's actually an English thing. If you put AO or EO or OO next to each other, they don't have the vocalization you think they do, right? Imagine putting the O in monoxide. You would have MONOOXIDE. That would not read as monoxide. If you tried to read that, it would be monoxide, because the double O has the ook sound, which sounds stupid. So the rule is drop one of the O's. So it sounds like monoxide. That's why the rule's there. It's really because it sounds dumb. And so that's why they do it. Alright. So, ionic compounds, you get their formula units based on the charges. Right? Covalent compounds, you get the names based on the number of them present.
So how do you know if one's covalent and one's?
Covalents will be 2 nonmetals. Ionics will be metal and a nonmetal. And you're like, which ones are the nonmetals, Dr. Ireland? Everything to the left of that line, or sorry, right of that line is a nonmetal. Everything to the left of that line is a metal. So if you got 2 things, if you got one thing from there, one thing from there, ionic. You got 2 things from over here, covalent. Now, what are we going to talk about tomorrow night? Polyatomics.
Oh my gosh.
So no notes are allowed on the test because I don't think I would.
I'll give you a sheet of notes. Have a sheet of notes, I don't care.
Really?
Yeah.
Because
Have a sheet of notes.
Oh my gosh.
You can condense it down to a sheet of notes, right?
Yeah, front and back, yeah.
yeah, that's a sheet, that's a sheet.
You'll do the Mobius strip thing, where you turn into a Mobius strip, so it's just one side all the way around. I had a friend who did that in college. So you said one side of notes, so you made it a Mobius strip. It's like, it's one-sided. All right, oh good, you got a shot of my belly right there. It's awesome. All right,
Now I feel better.
so that's it for today. Tomorrow, what do we do, 9 o'clock? 9 o'clock tomorrow night, there'll be a Teams meeting. I will send a link so you can ask questions. What we'll talk about is the last part of this, which are polyatomic ions, which are essentially just covalent groups that have a charge.